doing really is starting section 3.3, which is a continuation of chapter 2, where in chapter 2, we studied one-dimensional motion, motion left and right, or motion up and down. Whereas in this section, what we're going to do is take a look at motion that's up and down and left to right, both. So think about any real-life example of an object being thrown. Any object that's literally thrown across the room has to move in 2 dimensions. Nothing will move really in 1 dimension perfectly. Even if I drop this, it kind of moved to the left a little bit when I let go of it like that. Nothing's going to fall perfectly, I mean, unless it's a perfect free fall in a closed experiment. But even if I wanted to throw this ball over to Liam, and I threw it directly at him like that, when it was coming toward Liam, the ball was descending, right? And he made that nice quick grab there. So do it again, right back. So what we notice is it looks like it's maybe linear, right? It looks like it's a line drive in a sense, you would say in baseball, but every ball really has some sort of vertical trajectory. So in this section, even objects that maybe get shot horizontally, like imagine shooting a bow and arrow. You know, when people used to hunt animals with bows and arrows, they'd have to look at the arc of the trajectory. Because the arrow, after a certain distance, would start to fall over, wouldn't it? So if you want to shoot a deer or shoot an animal that's running for, some sort of, sorry for any vegetarians, but if you want to shoot something for food and you were like a hunter-gatherer, you would have to aim a little bit high. Because the object would naturally, the bow itself, or the arrow itself would come out of the bow and it would descend. Remember how many people went last summer, right? Did any of you guys go last summer? Yeah, and the camp. In the bow and arrow, you always had to aim a little bit higher than where it was going to land. Because if you don't shoot it off with enough velocity, it's bound to start to fall a little bit. Even if you shoot it like a speeding bullet, it still falls. You could take an actual gun, shoot a bullet perfectly horizontally. It will go a lot further than a bow and arrow or an arrow would, but eventually it would fall to the earth.
It slows down.
Okay, it slows down, and because gravity pulls it to the earth. Both those reasons.
Then why do you aim lower with that? Like when
I'm guessing because of the kickback. There's kickback, and usually your target's not 1,000 yards away. If you're using like a sniper rifle and you're shooting, you actually have to account for the descent of the bullet. You have to account for the curvature of the spin and stuff. There's a lot to it. But in general, objects are going to fall down. Yeah, maybe there because it has a little kick. There's a little, what is that called, recoil? Yeah. So I'm guessing that's why. But in general, objects moving in the horizontal direction will fall vertically as well. Okay, so that's what we're going to look at here in this section. We're going to talk about the shape of parabolas as our shapes, which you're going to see in your Algebra 2 trig course, if you haven't already. And you already have, perfect. So you know what the general shape is. So the shape of a parabola is what we're going to be looking at. Stuff as well. So let's first define 2 things. A projectile is any moving object that can be modeled as a point in space. Okay, any object that could be modeled as a point in space. Projectile motion simply means 2-dimensional motion. And then notice I put, or free fall, with initial horizontal velocity component. What the heck does that even mean? Let me explain. So this is free fall, right? That's what free fall is. So that's free fall. That's not projectile motion. It's only 1-dimensional. But if I were to take this tennis ball and roll it off the table, technically speaking, it's only got velocity in the horizontal direction because it's moving left to right. So the vertical velocity is technically 0 to start. So this is actually a free fall, but a free fall with horizontal motion involved. Think about it for a sec, ready? As it's rolling, the velocity cannot be up or down because it's moving which way?
left and right.
Left and right. So the velocity right now is only horizontal. Even when it departs the table, it's still only horizontal. Even when it's about to leave the table right here, it's still only horizontal. Then it starts to descend and picks up vertical velocity. So in this chapter, we have to differentiate between vertical velocity and horizontal velocity. That's why we did all that stuff with trig. I know, it just blew your mind. I saw that. So we're going to have to use that. The whole entire chapter, this concept of vertical and horizontal velocity.
Oh, because it makes a triangle.
And yeah, very good. That's where the trig comes into play. You see the triangle already? Okay, this is like your vertical component, horizontal, resultant. That's what we've been doing over and over again. Okay, so let's continue. So we talked about the path of a projectile. Now, what if I asked you the following? In the diagram, label one of these as real life and one of these as the simplified physics version. Which would be which and why? You have to think about it. Don't just answer right away. Which of these would be like a real life situation? Which of these would be what we consider in physics to simplify things? And why? You don't pick up on this. It's not easy to see.
Would the black one be real life and the blue one be?
Why?
Because when you simplify it, you don't account for the friction that they are applied.
That's exactly right. Very good. This is what we're going to be seeing in physics class, where it's a perfect projectile or a perfect parabola because you ignore air resistance or friction. But when you include it in real life, this is the actual path with air resistance. Okay, we should all know by now that an object moving through the air, free to move, not a jet plane in the sky or something, but an object moving freely, can only be slowed down by air resistance. If air helps it, it's not really air resistance anymore. So if like a gust of wind comes by and helps speed this up, it's not really air resistance. That's more of like a tailwind. Okay, so the actual object is pushed forward. But air resistance will slow down the object. So the shorter path takes into account air resistance. We are going to assume air resistance is 0 in this class, simply because to calculate it, we need a little more knowledge than right now when you study the math. You've got to get through a little bit of calculus before you can start including air resistance, because it involves what's called the differential. Okay, a term in calc that something that you haven't learned, and even calculus students in Mr. Linus' class are only just learning about it now. Okay, so we're going to assume in our class that there is no air resistance. So we're specifically talking about this perfect parabola here. Okay, not the one where it gets shorter because of air resistance. So let's take a look now. Okay, at this example that we talked about, right, over the tennis ball a moment ago. Can I get a volunteer, or 2 volunteers actually? I'm going to need this. I need 2 volunteers for this. All right, Chris and Francis, come on up. Chris and Francis. All I want to do, okay, I appreciate all those that volunteered. Most people don't always volunteer as much. That was so cool. I'm actually really happy about that. Nice. All right, so here's what I want you to do. One of you needs to roll this off the desk. Okay, so we'll use this as the example. Ladies first set. Okay, let's click the locks on here. On that side, just click the locks. Oh, is it plugged into the floor? It is plugged into the floor.
You want me to go?
No, it's alright. Yours is also plugged in. I plugged all these in last week for the engineering class. That one is true. The middle one is not. We go to the middle. Alright, let's figure this out. Actually, we can do it right here. So what's going to happen is this. One of the 2 of them is going to roll one of these objects, maybe starting over here, and we'll roll it this way. The other person is going to drop the other object the instant this one falls off the table. So this one's going to be rolling, okay? As soon as it's about to fall off the table, when it gets to literally the surface here, like where it interacts with the edge of the surface, this other person is going to drop this ball from the same height it would fall from. Does that make sense? Does that make sense? Okay? So you want to roll, you do the person rolling, you do the person dropping. Okay, so what you're going to do is put it on the table and just literally slide it off to the edge and you're going to drop it over here. Okay? So you could be off the table already. Go with yours, maybe in here, and go a little bit faster. And just listen. Just listen, please, carefully. Did you hear almost only one bounce land? There's a tiny difference because obviously human error or human reactions can't respond that quick. Not really in general. So hold yours off a little bit. Go back. Go over time. It's a tiny little time difference. Now, theoretically, what do you think should happen?
Well, I think that the one speed in the beginning would fall down fast.
That's what you would think, common sense, because it has velocity, right? But as physics students, knowing that this object is only moving horizontally, and we're trying to find the time it takes to fall vertically, what do you think should happen between the 2? They should fall at the exact same time. But let's go over this one more time. Go ahead, Francis, one more time. Go a little bit faster. Go toward like right here. Okay, so your ear is almost identical over there. The reason, let me go over this. Thanks. The reason is this. When this object is falling like this, right, when this person lets go, what's the initial velocity?
0.
0, right? That's the initial vertical velocity. But we haven't been using that term. We just keep saying initial velocity. But technically, the initial vertical velocity is 0. Well, when I roll this off the table, as soon as it leaves the table, it starts to fall. It has initial horizontal velocity because it's moving. But the vertical is 0 still because I'm not throwing it downward, right? Watch, if I do this, then I've got some initial vertical velocity, whatever that is, -2 meters per second. But if I just drop something, it's the equivalent of rolling something horizontally and dropping at the same time. So if I drop something, as soon as this falls off the table, it's like this one is falling vertically finally, and this one is only falling vertically. The one that's rolling off the table, though, what does it also do? It moves out from the table because it's got horizontal velocity. So although I drop this and it takes the same time to land, the one that was rolling falls a certain distance away from the table. So that's what you're seeing here in this diagram. And there's actually a device that, like some lab, you can buy like lab supplies as science teachers, and there's a lab that they actually sell this device. And one gets shot horizontally, one gets dropped at the exact same time. And you hear that land at the same time. You have 2 tennis balls, you can demonstrate the same thing, but without as much precision, right? There's a machine that literally does this. It literally just drops that at the exact same time the other one gets launched horizontally. And you can create an apparatus to do this. You can make something so that there's a device where you push a switch, and as soon as you push the switch, it launches something. You use a spring-loaded mechanism, and while that's happening at the exact same time, a little gate opens up, and the other object drops. So they both go off at the same exact time. But the concept here is literally, look, at every one of these points. Look here. This matches up with this. This matches up with this. They all match up throughout the process. This is a time lapse or like a slow motion version of this object. This one being dropped, this one being launched horizontally. Now, obviously, this one travels some displacement in the x direction. Right? There's some horizontal displacement for the yellow one. What's the horizontal displacement for the red one? 0. The horizontal displacement, remember, is how far it moves this way. The red one was just dropped, so it did not move left to right. So the red ball on the screen, its horizontal displacement is 0. The green one, it has some value. Now, what's important is this. The time is the same for both, for this to fall. Okay, again, because the vertical initial velocity, we'll call that VIY, is 0 for this one. Well, over here, the vertical initial velocity is also 0. It's the horizontal velocity that is some number. Okay? Again, the vertical velocity for the red object is 0. Well, the green object, its vertical velocity is also 0 to start, because it's only moving horizontally. It gets launched horizontally. So that's some number. But this has no horizontal velocity. This is a true free fall. 0 vertical, 0 horizontal. That's this right here being depicted in red. But the green one is shot out horizontally. So we have to consider the fact that it has some value of initial velocity in the x direction. Whereas the y direction, its velocity is 0. Okay? So we're going to see the beginning of this section, and we're going to see that the angles are not as much as necessary. It's the second half of this section where we're going to utilize those angles. Okay, so let's take a look at this. So example 1, a bridge is 300 meters above a river. Tom Cruise jumps off the bridge to avoid some sticky situation he's gotten himself into. He jumps off the bridge by running off the edge of the bridge in a horizontal direction. So imagine that your desk is the bridge, and he literally just runs right off the edge. Like he's running from somebody behind him and he runs right off without noticing. It's the same thing as the tennis ball falling.
It's like a bird, like stays there for a second.
Yeah, you ever see those cartoons where like the roadrunner runs off a platform and he like stops and he's like, and then tries to get back and then you see him fall. Why the coyote? Or
this roadrunner gets across the top.
You're right, coyote chases the roadrunner. That's the whole idea. So yeah, with the Wile E. Coyote, he realizes he goes off the edge of the cliff and he looks back and he tries to reach for the cliff, but he just starts to fall. Obviously, he would never pause, right? But in reality, he would run right off the cliff and it would be the tennis ball rolling off the table. So it's just like a free fall. This is a free fall, but with some push in the x direction. But in the y direction, it's a free fall. Okay? So we're going to approach this problem and figure out that if the horizontal displacement from the bridge. He lands 50 meters from the bridge in the water. What is the velocity? What is the velocity with which he jumped? Okay, so if I drew a diagram of this, I'd have this person running this way off of a cliff. He then follows this path, right? Some sort of half parabola, because it's not, remember, we're not launching an object this time. The object is rolling off the table. When it rolls off the table, it falls with some parabolic motion, but it's more of a half parabola than a full parabola. Okay? So that's literally what this is doing. The tennis ball is rolling off the table and it will roll like that. That's what Tom Cruise is doing. To answer these problems, what you need to do is separate the vertical and horizontal components. So let's make a little like T-chart. Let's split up our page. We know that the bridge is 300 meters, by the way, above the river. And he lands out here, which is not drawn to scale, 50 meters out. Okay, this is not drawn to scale, obviously. Okay, because 300 is clearly more than 50 there. Okay, not drawn to scale. Now, we've got two directions to take a look at. Our x and our y direction. You could write horizontal and vertical if you'd like, or just write x and y. Either way works. Okay, but we have two things to worry about. In the x direction, what do you know? What do you know about horizontal parts of this problem? Give me something horizontally about this problem. I can't hear you. He moves horizontally after leaving the bridge 50 meters. So what variable would that represent? Good. The horizontal displacement x is 50 meters. And he moves to the right, so it's positive 50 meters. In our diagram, at least, right? What else? What do you know about the vertical direction then? The vertical direction, LT.
So that'll be negative 300.
Very good. And notice LT recognized the negative because he's moving down. Okay, it's got to be negative. If you get that negative, this problem will not work. Okay, it literally will not work. What else do you know now? Those are the easy parts for sure, right? Because it's on the diagram, which helps. What else? What are the keys, Carol?
You know the total displacement?
You really don't, because it's a curved path. You can't use the hypotenuse here. But I like the idea. You could figure out the hypotenuse, but that is not the distance traveled, because this person follows some curved path, so it's not a direct line. But I like the idea.
The vertical acceleration.
The vertical acceleration is always gravity. Good. The acceleration in the vertical direction, I'm going to call that AY. I'm going to put a little subscript with a little y there. And that's negative 9.81 meters per second squared. Siobhan, was that what you were going to say? Okay, there's more though. Can anybody else tell me more about this? Yeah. Not for the horizontal, but the vertical. Let's go over this. So remember, the tennis ball is moving which way right now? Good. This is Tom Cruise running back and forth. Not sure what he wants to do. Going crazy as he always does. So he's trying to figure it out, and then all of a sudden he decides, oh no, I'm just going to run right off the bridge. So when he runs off the bridge, he can still move horizontally to start, right? So he's got some horizontal velocity. We don't know what that is. But we do know in the vertical direction, he was not moving. So the vertical... But put VIY there, please. Okay, in the vertical direction, Tom Cruise is not moving. Remember, he was literally moving left to right. When he jumps off that bridge, imagine he just runs right off horizontally. He's not jumping at an angle. He's not diving down into the water. He just runs right off. Okay? Yeah, who would ever do that, right? Run right off?
Would you be able to find the acceleration of the object? Would you be able to find the acceleration of x technically? Because you do like
remember, we're saying that in the x direction there's no acceleration because there's no air resistance.
Oh.
If we included air resistance, we'd have a sub x. But a sub x is always going to be 0. Okay, the acceleration in the x is always going to be 0. The reason is this, ready? Here's Tom Cruise running with a constant velocity right off the bridge. Okay, he's not running with some accelerated velocity, and it wouldn't even matter. If he started running slow and accelerated while running still, it's the instant that he falls off the bridge, that's his initial velocity. Whatever the velocity, let's say, ready? I'm running on one side of the bridge, 2 meters per second, 3 meters per second, 4 meters per second, 5. And when I hit 5 meters per second, I run off the bridge. That's my VIX, 5 meters per second. I don't have to worry about acceleration. I don't care if he accelerated prior to that. What matters is from when he gets launched off the bridge. When he gets launched off the bridge, he's got some initial velocity. That's what we're trying to figure out in this problem.
But wouldn't he have acceleration if he's like running fast?
Prior to falling off the bridge, sure. But imagine, right, if you're running with a constant velocity, what's your acceleration? It's 0. Remember, constant velocity means you're not accelerating. So I could be running across the bridge with a constant velocity and run right off. My acceleration would be 0. Even if I'm speeding up, as I'm running across the bridge and getting faster, it's the instant you leave the bridge. That's the velocity we're concerned with. So that velocity, that instant beforehand, is what we're trying to figure out. Okay, that's what we're trying to figure out in this problem. What don't we know that is involved in this problem in both the x and y direction? There's another variable that we haven't talked about yet. Aiden?
Well, I was going to say we don't know how much he ran before the jump.
Correct, but that's only the x direction still. There's another variable that involves the x and the y direction. And it would be useful for us to know that, Christina. That is also involved, you're right. But that's not going to help us. But final velocity, you could find in x and y direction. This is going to be tough to find those. Time. The time it takes for this object to fall is the same in both directions. If I throw this object off here, right, the time it takes from when it leaves to when it hits the ground. If I find the time in the x and I find the time in the y, it's the same thing. It's time, it's time. You can't break up time into components. So let's write this down. Time is unknown, but since it's on both sides, we can call this our linking variable. I call it the linking variable for a reason. And you're going to see another thing this year that's called the linking variable also. The reason it's called the linking variable is because it links the directions together. It's the one thing that is constant in both x and y directions.
Is this always true for everything?
Yeah, for any two-dimensional problem, time is always your linking variable. So what we need to do, really, and this is where it's going to get a little bit tricky, but you got to go back to chapter 2 and think about those formulas we learned. We're going to relate the x and y directions to each other, but we're going to solve them independently first. So, remember a moment ago when I had Chris and Francis roll the tennis balls? We said that the time for a free fall, ready, is the same as the time when it's moving horizontally initially. So what we can do is we can find the time over here as if it's a free fall in the y direction. We'll do what?
Make it equal to that.
And then we can find VIX. So let's go to the y direction first. There have been so many sirens today, it's unreal. Can somebody do me a favor, close that window? Let's turn the air on for a little bit, maybe. I guess, seriously, they're after me. 77, yeah, it's the Lenox Hill. But today, I've been teaching in this room, like, this is like the 10th time the sirens went off. Okay. So, in the y direction, what am I missing that I don't know at all in this problem? There's something I don't have at all in this problem. Christina mentioned a little while ago. What was it? Yeah, you have no information about final velocity, which means that you're probably not going to use VF equals VI plus AT. You're not going to use VF squared equals VI squared plus 2AX or 2AY, depending on the direction. So you're probably going to use that third formula. That third formula says, either, depending on the direction you're in, x or y, it depends, y equals VI t plus 1/2 a t squared. Notice I'm starting to put subscripts everywhere now. Why am I doing that? to distinguish between vertical and horizontal velocity and vertical and horizontal acceleration. So these little y's you see are not variables, they are subscripts. They're identifiers. Okay, again, this is not a variable, this is not a variable. This is a variable y. This is a subscript, meaning velocity initially in the y direction, acceleration in the y direction. Why don't I need a subscript for time? Sam? It's the same for both of them. Good. It's the same unknown value for both directions. So if I call it ty and then tx, they're the same thing now. So in this problem, I could go ahead in the y direction and drop this off right away. Why can I do that? Because what is 0? Yeah, initial vertical velocity. Remember, this, take a look again, is the same thing as a free fall in the vertical direction. So you could literally approach this problem like you were a free fall, even though little Tom Cruise is running off that bridge. So we could find the time it takes, go ahead and solve for that, find the time it takes for this object to hit the water in the vertical direction.
When does the quadratic equation start coming in?
When we have VI's, which is going to probably be in a little while. It'll be in this section for sure, but we may or may not get to it today. I want to do a lab in the second period. I don't want to do a double lecture, so probably not going to get to it today. If I were to solve for t in a formula, I'd get rid of 1/2 by multiplying by 2.
Yeah.
I would get rid of a by dividing by a. Thank you for ever agreeing. I think, was that you, Aria? So I divide by a next, and that's ay, I should really put, right? Ay every time. And then take the square root, please, at the end. If you take the square root of both sides, the square root of t squared is just t. So the square root of 2y over a is our answer for the time it takes this object to hit the ground. You did this in test 1, whether you realize it or not, so we just didn't have subscripts that way. So that's what it looked like. Test 1 was a problem where an object was dropped from rest. You had to find the time it takes and all this. This is the formula you could have used. It actually was nailed, right? Remember? You headed the ball up in soccer, and we said how long does it take for that object to return back to the ground? And you could have simply used this equation right here. These equations are not going to go away. So if you struggled on the first test, it doesn't mean just ignore this. It means that we have to correct any errors that happen. Plugging in. Okay, that's what I'm going to have right there. Plug in your values, please. See, if you forgot that this was negative, what would have happened? Yeah, the time would have been imaginary, actually, because it would have been under the bracket. Imaginary. Have you learned about imaginary numbers yet?
Yes.
You would have had a negative under the radical, thus imaginary. It is not, though, clearly the case, so we get an answer, which is? Nick?
7.82, sorry.
Thank you, Nick. 7.82 seconds is the time it takes. Now, again, back to this example with the tennis balls. If it takes this tennis ball 7.82 seconds to fall, it takes the same tennis ball moving horizontally 7.8 seconds to fall, assuming they fall from the same height. So I can literally go like this, right? And they hit at the same time, even though this one was moving horizontally first. So this time that it takes is the same time we're going to use now in the x direction. So let's go back to the x direction. Go back to the x direction now. I have to slide this down so you can see it. So the 7.82 we could put in right here now. That was in the y direction we did all that work. That's why I was doing it on this side of the page.
But it obviously takes longer. I mean, as a ball, it's the same time, but this.
It takes the same time though. It literally takes the exact.
Because even if you like drop it first and then like at the
If I had a precise mechanism to do it, it would literally hit the ground at the exact same time. Because think, what causes an object to fall to the ground? Which acts in what direction? Which way? Vertical. The horizontal motion in the beginning has no effect on the vertical velocity. So it's the same exact thing. Like if I drop these two, they should hit at the same time. Maybe they didn't because of other things, but they should just drop. If I even move it horizontally though, it's not affecting the vertical velocity because it's moving horizontally. If I do this though, Sophia, that is different than this, right? Because that's going to be in the air for a lot longer. But if I were to literally, if I could somehow do this, where I was able to go like that, and they actually moved at the exact same time and left at the exact same height, that ball should hit the ground at the exact same time.
But if it can't with vertical time.
But if it comes off with any vertical motion, if you throw it down, if you throw it at an angle, if you throw it only horizontally, this works. If you throw this at any angle, which would give it some vertical velocity, this will not be true. It's only when something is fired horizontally that this is true. Okay? That's the only time that this is going to work this way specifically. Where did I put my pen? There it is. So we use that time in the x direction. Now, in the x direction, I told you a little while ago that we're going to assume acceleration is what?
0.
In the x direction, right? So when there's no acceleration, there's only one formula that you're going to ever use. The first formula we learned all year. Sam? Okay, there it is. This is the formula you will use all year for the x direction. V equals x over t. Why can I use that? Because there's no acceleration. Okay, there's no acceleration. Now, if there's no acceleration, what else do you know about the velocity if there's no acceleration? It is what? What's the term? A constant. The x velocity is always going to be the same throughout the process of some fall or some projectile horizontal motion. So if I do this, and I roll it, right? And I roll it with a velocity of 2 meters per second. Even while it's falling, its horizontal velocity is still 2 meters per second, 2 meters per second, 2 meters per second, because there's no horizontal acceleration. Remember, when horizontal acceleration is 0, the velocity is a constant. So we could even call this v bar if we wanted to, meaning constant. Focus, please. We could call it v bar if we had wanted to. So for this problem, if we want to figure out what that velocity was that Tom Cruise left the bridge with, just take 50 meters over the time you got, 7.82 seconds. That will give us the velocity, and you could put v bar x or vx or vix. They're all the same thing, really. I'm putting a little bar over it because it's ended up being constant. This velocity is the velocity that Tom Cruise ran with off the bridge. That will not change in the x direction. Remember, when an object is falling, the vertical velocity changes. The horizontal never changes. Write that down. The horizontal velocity will never change because acceleration in the horizontal is 0. So even while he's running off the bridge, his horizontal velocity is still whatever this answer comes out to be. Even as he's hitting the water, that's still his horizontal velocity. What does that come out to be? Siobhan?
6.4 meters.
Very good. Meters per second because it's velocity. That means, ready? Here's Tom Cruise, aka his tennis ball. He is running with 6.4 meters per second. He runs right off the bridge. He starts to do this. Well, he's picking up velocity in the vertical direction. He's getting faster. But in the horizontal, this is still his velocity the whole way through. Okay, in the second period, we're going to do a lab now. Now, before I give you a 3-minute quick break, over the next 4 or 5 days, I put up homework. The homework is to get started on the problem set. Next week, we're going to finish 3-3 on Monday. Or Tuesday, I forget which day I see you guys. But we're finishing it next week. Then we're going to have our test, I think, is at the end of next week. It's really pretty much 3-1, 3-2, and 3-3. That's it. So in the next 4 days, you need to do the problem set for 3-1, 3-2 to get those out of the way. And then try to start your homework for 3-3. You could do the beginning problems from the homework where it's fired horizontally. When it's fired at an angle, those are the ones that we haven't gotten to yet. Is that clear? Yeah. So you're not going to start those problems yet. When we get to the angular stuff, which we're going to do in the next class, we'll talk more about that. Okay, there is a second example. A C-130J Super Hercules plane flying 500 meters above the ground needs to drop an air package to soldiers on a remote island. This is physically how it's done. Okay? If the velocity of the plane is around 186 meters per second or 670 kilometers an hour, when it drops the package, how long will it take to reach the ground level? How far will the package travel horizontally before it lands? So we've got this, right? We've got a plane up in the sky. Wonderful image. Okay, it's traveling horizontally. That's pretty good, right? It's traveling. Say yes. We're traveling. It's traveling with a. Oh, it kind of is a dolphin or a fish. I always get fish and planes confused. They look similar, you know? So the velocity the plane is traveling with, right? Now, the person in there does what? He or she just goes, you know what? I'm going to drop it. I'm going to drop the package. So here, watch me. Ready? I'm the plane. Okay, I'm the plane. I'm the plane. I'm the plane. I drop it. Isn't that the same thing as rolling off the table? Because which way am I moving right now?
Horizontal.
And then I drop it. So it has some horizontal initial, but it doesn't have any vertical, right? I'm not throwing it down. I'm not throwing it at an angle with some vertical velocity. I'm not tossing it up like that, waiting for it to come back down. I'm moving horizontally and dropping. And it follows that parabolic path, the same thing as that. So this problem is identical to the last problem. Okay, we're just going to change some things up, find some different variables.
Right, but like, so let's say that the plane was, you know, it was slowly going down, or the cliff that he fell off had a slope.
Again, then it's not one of these problems. And then
Right.
we have to.
But I'm saying
we're going to approach that differently.
So the only way that these problems work is if the
Horizontal.
they're going has to be fully horizontal.
Yeah, absolutely. Okay, so with that said, the package that's being dropped, because of like basic laws of physics, is moving at 186 meters per second also. If the plane is moving that fast, so is the package. So when the person drops the package, it's got some horizontal velocity of 186 meters per second. So when we're looking at our diagrams now, and our xy, we can automatically say that Vix is going to equal 186 meters per second. Last problem, we determined Vix, but now we're given that value. How far above the ground is it? That? So y equals negative 500 because it's above ground and it's going to travel which way? Down. Our goal is to find what? How long it will take to reach the ground. That's time. And how far it will travel horizontally before it lands on the island. So we're going to eventually have to figure out time. And we're going to have to figure out x. Both of those. What else do we know about this problem? If it's only moving horizontally to start, what is VIY? Yeah. Again, remember, this object is the same as what Benno and Franken were demoing with the horizontal motion. It's only moving horizontally, so the vertical component of velocity must be 0 to start. In the x direction, we know acceleration is always 0. And what is it always in the y direction? Anybody? There it is. Okay, a number that I told you, I wasn't joking, you don't have to memorize it, but you probably will. You probably will memorize it. So look at the y direction. Isn't it the exact same problem as the last problem? So what should you do? Should you go through that whole solution again?
No.
Heck no, you shouldn't. T equals radical 2y over a. That's the answer. It's the same exact problem. Do you see how the beauty in physics problems exists? Different scenario completely. Now we're trying to find out horizontal displacement, but the y direction is analogous to the last example. So please don't redo the y direction. You could write y equals VIT plus 1/2 AT squared. Cross off VIT again and solve, but you will get this. Noting that that's a little subscript for y. Okay, again, if you need to see where this came from, this is the exact same solution from the last problem in the y direction. We drop off VIYT and we solve for time. What do we get when we solve this one for time? By the way, any free fall will use this, right? Look, I do this right now. What's the height? Maybe 2 meters? put a 2 in for y, or negative 2 in for y here, for minus 2 meters, you could figure out the time it takes to land. Okay? You could literally find the time it takes to land for me just to drop this by just plugging in whatever the height is for y. This always works for free falls. What do you get when you plug in negative 500, the height from the plane when it drops it? What do you get? 10.1. Others? It's going to be more than 7, because last problem was 7 something, and it was only 300 meters, right, when it was falling? This is falling 500 meters now, so it's got to be longer than 7. Yeah, 10.1?
Yeah. Oh no, I didn't do it.
I'm just asking somebody else to confirm. Oh, thank you. Okay. So now that it's been confirmed, let's go over to the x direction. Well, earlier, we didn't know what the time was in the x direction, but the time is the linking variable. So what should you write down for time? 10.1, the same thing you got in the y direction. So although you may not be able to solve for time in the x, if you can solve for it in the y, just carry it over to the x and it becomes your linking variable. Now, we want to find the displacement. We can only ever use this formula. It's the only formula we're going to ever use in the x direction because acceleration is 0. So multiply by time to get x by itself. (186) times 10.1. What do you get? 18? 18.
1,086 times 10.1 is 1,878.6.
Oh, my rest.
What does that mean?
It's a
It's right.
It's a bad habit.
I've just been hearing a lot of it lately. That's what I didn't know what it meant.
It's like a chicken round.
Never heard that stuff. Is it even a word?
Yeah.
To rouse up the crowd doesn't mean like to get them like rowdy?
It's an actual word, but the way I'm saying it is it's like a big scroll up. It's like
Yeah. Someone
So, what we determine is this. I want to make sure we understand the significance of our answer. This is the important part of physics. Forget the math for a second. The important part is the significance of this answer. Here's the fighter jet, or the Hercules jet that's going to drop a package, right? Why do we care about the x value? Why is this important in this problem? Think about it logically. Theo?
Because if they were going to drop a package, they want to know where it's going to land.
Yeah. If I'm flying that plane, I need to know if my engineer in the back tells me, all right, in 3, 2, 1, drop. Well, why did he tell me to drop in 3, 2, 1? Because he was estimating the time until it was exactly 1,878 meters from the island, and obviously there's room for error because the island is relatively big, but not much error. There's not too much room for error here. So when the island's here and the package is here, it knows to drop so that it will land on the island. Okay, so you're literally determining, the location from the island that you should drop it so that it does this and lands smack on the island. Theo?
Wouldn't it have a different acceleration?
It would. And remember that we are physics students in 11th grade, and engineers in the military know how to incorporate air resistance. Absolutely. Absolutely. Okay, there would be AX in a real life problem. You would have some acceleration in the x direction. It wouldn't be this simple. Does that make sense? We've modeled it to be simpler because the knowledge is involved in calculus that is something you haven't learned yet, so we just can't.
How would you then put those two together and figure out where to drop it? Like the AX and the AX?
Well, the AX you would have to consider in the problem. You could no longer use an equation like this to determine it. You'd have to use x equals bit equals 1 half at squared and solve for time, but it would be a quadratic. It's not hard. You could do it, but the issue is that to get AX, you need calculus, just to get the number, whatever it is. Depends on the size, the coefficient of friction, the velocity of the wind. There's so much that goes into play. And you can't calculate AX without knowing. Okay?
Exactly.
Listen carefully. I want to talk about a few things now. There's a lot that you need to do in the next 5 days. So either take out your planner or remember this. There's a lot of stuff for you to do.
Is it on the doodle?
First, these two things are on Moodle, I'm about to tell you right here. On Moodle, I already wrote, next week we get back, we finish 3-3, we do our lab, at the end of the week is your test, it's on 3-1, 3-2, 3-3. So, over the week, you should do problem set from 3-1 and 3-2, which you can do at this point. If you're struggling with 3-1, 3-2, maybe you have to wait, but try at least. You could start the homework for 3-3. It's not due when we get back, but about half the problems involve only horizontally launched objects. If you see a problem in homework 3-3 that says it's launched at an angle, you shouldn't do it yet. Does that make sense?
Yeah.
Okay, those two things you need to do in the next 4 or 5 days. What else do you have to keep considering that we can't forget about?
November 5th.
Yeah, your projects. Keep your projects in mind. Okay, all the supplies are ready for me to build this ramp once I just have time to put it together. I've had no time. But I've got all the supplies, I cut all the wood, so I'm going to make that ramp at some point next week. I need to get the hinges. I'm waiting for Amazon to deliver them. Okay? I forget, to be honest, Katie. Take a look. I think it's at the end of next week, I think. Okay?
Mr. Howell,